Okay, so hybridization is a way of explaining how atoms come together to form bonds. So if we take a look at, say, hydrogen chloride, so hydrogen has one unpaired electron, chlorine has one unpaired electron, so it makes sense why they would come together and form a bond, because electrons do not like to be unpaired. So boom, there you go, you've got a bond. All right? But, and this also explains why things like neon is 1s2, 2s2, 2p6. Neon's got all paired electrons. So neon doesn't form a bond. Argon doesn't form a bond. So it explains it really nicely when you look at it this way. But what if you have something like beryllium? When you look at beryllium, beryllium has two electrons, right? It's 1s2, 2s2. These two electrons are paired. So when I look at it, I would say that beryllium wouldn't bond with anything. Its electrons are already paired up. That's why neon doesn't bond. So why would things like beryllium and magnesium bond? Because its electrons are already paired up. So we have to come up with an explanation as to why these guys bond, because I know that beryllium hydride exists. I know that magnesium chloride exists. So why is it that beryllium is bonding with two hydrogens when its electrons are already paired up? And that's where hybridization theory comes into play. So this is what we think is happening with hybridization theory. Beryllium is got the following configuration. Okay, so this is before it bonds, and it's happy. Okay, but when it gets near the hydrogens, we believe that one of its electrons gets excited and jumps to the higher level. And then we believe those orbitals hybridize. Okay, so what hybridize means, I can't write, here we go, there's something wrong with my iPad. Okay, hybridize. What hybridize means is that I'm going to mix two things together. So if you hybridize a lion and a tiger, you get a liger. If you hybridize a horse and a mule, you get a donkey. If you hybridize red and blue, you get purple. If you hybridize yellow and green, you get, or yellow and blue, you get green. So I am going to hybridize an s orbital Now, if you remember, an s orbital is a sphere. So I'm going to hybridize a sphere with a dumbbell. So instead of mixing colors, I'm mixing shapes. So what will I get if I mix a sphere with a dumbbell or a p orbital? What you get is what's called an SP, and it looks like a kidney bean. One of them's facing this way, and the other one is facing the other way. And we call them SPs, okay? because they're a mixture of an S and a P. And because I mixed two orbitals, I get two of them out. The other p orbitals that weren't involved are still there. Okay. Now electrons want to go in the lowest available orbital. So my two electrons will go there. Now when I look at beryllium, I see that I have two unpaired electrons, and I would need two more for a total of 4. So I would say that beryllium would be following the rule of 4. Now it makes sense why the beryllium would form two bonds. And that indeed explains why I end up with this sort of configuration. There's 4 electrons around the beryllium, so it follows the rule of 4. And I would say the hybridization on the beryllium is sp. Okay? Let's do another example. Suppose we've got aluminum chloride. When I look at the configuration for aluminum, I see it is aluminum is neon 3s2, 3p1. So I only have one electron that's unpaired. So I could see how aluminum would form one bond, but why is it forming 3 bonds? So we have to come up with an explanation. And what we believe is happening is that the electron gets excited and it jumps up to the 3p. Oops. And when it does this, I now have 3 unpaired electrons, so I'm going to hybridize an s and 2p orbitals. So now what happens when I hybridize an s orbital which is a sphere, but now instead of mixing one p orbital, I'm going to mix 2 of them. So what do I get out when I mix a sphere and 2 p orbitals? Well, what do you get out when you mix yellow and 2 parts blue? Well, it becomes more blue in nature. It becomes a darker green or turquoise. Okay? So similarly, what you get out is now 3 kidney beans, and these 3 kidney beans are at 120 degrees from each other. And yes, it gets difficult drawing these. And I will link you to some videos that actually do a better job of drawing it. All 3 of these are called sp2s because I involved one s and I involved 2 p orbitals. So it's an sp2. We do not write the 1. Okay? And since I hybridized a total of 3 orbitals, I end up with 3 lines, and I still have that P over there, which I did not use. So it's right there. And something to keep in mind is this 2, that superscript, now refers to the number of orbitals, not the number of electrons. So I hybridized 2 P's. That's why it's a 2. Whereas when we are talking about electron configurations, the superscript means the number of electrons. So it means I've got 2 electrons in the S and 1 electron in the P. So electron configurations, the superscript means the number of electrons, whereas hybridization, the superscript means the number of orbitals. Now we can understand why aluminum forms 3 bonds, because I need 1, 2, 3 more electrons. So I need 3 more electrons for a total of 6. And now the aluminum would do this. All right. There we go. All right, let's do 2 more examples. Let's do methane. So carbon is 1s2, 2s2, 2p2. It looks like everybody's paired up. But if we do the orbital diagram, we see that we actually have 2 unpaired electrons. So I could see why methane or carbon would bond with 2 hydrogens, but why 4? Well, once again, we believe that the electron becomes excited and jumps into the higher level. And then we hybridize. And when we hybridize, we are now involving 1s and 1, 2, 3 p orbitals. Not 3 electrons, but 3 p orbitals. So it becomes an sp3. The total number of orbitals I circled is 4. So I end up with 4 lines. Okay? Now, what do you get when you hybridize a sphere with 3 p orbitals? And then my third one is on the z-axis. So when you do this, you are becoming more and more P-like in nature. So now it's like mixing 1 part yellow, 3 parts blue. At this point, the orbital basically looks like a p orbital, except that you've got one normal lobe and then one tiny lobe, okay? And you will get 4 of them, each of them 109.5 degrees from each other. That is difficult for me to draw that on a two-dimensional screen, so I'm just going to draw one of them, and then I'll link another video, but this is an sp3 orbital. Okay? So 1, 2, 3, 4 electrons go there, and I'm going to need 1, 2, 3, 4 more electrons, so I'm going to need 4 more electrons for a total of 8 electrons. And this is why carbon follows the rule of 8. And has the Lewis dot structure like this. So hybridization explains where all those rules came from on Appendix F. We said carbon follows the rule of 8. The aluminum family follows the rule of 6. The beryllium family follows the rule of 4. Okay? I'm going to do one more example, and it's going to be ammonia. Now when I look at nitrogen, nitrogen is 1s2, 2s2, 2p3. So I have 3 unpaired electrons. So I could understand then why nitrogen would form 3 bonds and bond with 3 hydrogens. So I don't need hybridization to explain why nitrogen bonds, but I can use it anyhow. It still works. So if I started with my nitrogen, I could still say that the electron gets excited. But this time when it gets excited, it's just going to pair with another electron up there. And then when I hybridize, again, I am hybridizing the orbitals, not the electrons. So I'm hybridizing those. And I've got 1s, 1, 2, 3 p's, so it's sp3 hybridization. Okay? Actually, I want to do that in black. So I'm not counting the number of electrons. If you look up here, I've got 4 electrons in the p. So it's not the number of electrons, it's the number of orbitals, and that's why it's sp3. And in total, I've got 4 orbitals. Okay? Just want to space that out better. There we go. So I've got a total of 5 electrons, so 1, 2, 3, 4, 5. So I have 1 that's already paired up. I'm going to need 1, 2, 3 more for a total of 8. Okay? And so my nitrogen will bond like this. All right? And I will get this. And I still have my lone pair of electrons on the top. So the hybridization on that central nitrogen is sp3. the hybridization on that central carbon is sp3. The hybridization on that central aluminum is sp2. The hybridization on my beryllium is sp. Now before you start saying, oh my god, this is impossible, how am I going to do this? To figure out the hybridization on your central atom, all you have to do is be able to count the number of things that are attached to it. So, for example, there's 1, 2, 3, 4 things attached to my central carbon. So my hybridization has to add up to 4. So I can have 1s, and what's the maximum number of p's you can have? Whatever it is, I got to be able to add up to 4. So the maximum number of p's is 3. So it's sp3 hybridization. Okay? You can have 1s, you can have 3 p's, you can have 5 d's, and you can have 7 f's. Okay? So if we go to aluminum, there is 1, 2, 3 things attached. So my hybridization, I've got 1s. How many p's is going to add up to 3? Well, you guessed it, sp2. Right? 1 plus 2 is 3. So you don't have to go through this whole rigmarole. You can just count the number of things that are attached to your central atom to figure out the hybridization. Beryllium. So how many things are attached to my beryllium? Well, 1, 2. So my hybridization will be S, SP. 1 plus 1 equals 2. So my hybridization is SP. So let's just do another practice one at the bottom here. What if I had, let's say, boron trichloride. Okay, do the Lewis dot structure. Boron follows the rule of 6. Chlorine follows the rule of 8. All right. How many things are attached to my boron? Okay, I have 1, 2, 3 things attached to my boron. So that means my hybridization would have to be S, and then how many p's to equal 3? 2. So my hybridization on the boron would be sp2. Now you might say, well, Mr. Strauss, it says right here I got 3 things attached. Why'd you have to do the Lewis dot structure? Because I said the number of things attached. I didn't say the number of atoms. So if we look at ammonia here, how many things are attached to the ammonia? 1, 2, 3, and the lone pair counts as 4. So my hybridization is S, and it's got to equal, got to equal 4. So how many p's must I have? 3. Okay? So we could do this, for example, with water. Water's H2O. I do my Lewis dot structure. By the way, you're going to do the Lewis dot structure for water 1,000,000 times. So I get this. How many things are attached to my oxygen? 1, 2, 3, 4. So that means my hybridization has to add up to 4. So 1s plus 3 p's. So I have sp3 hybridization on my oxygen. Okay? And this time, if the volume doesn't record, like it did the first time I did this, I think I'm going to scream. All right. Peace out.